So, hi again. This is joint work with Marek, Kris, Nishant, and Kapil. So let me start slow with the standard classical bank account example. Right? You're keeping track of the balance of your bank account, and you want to implement a function for withdrawing an amount X out of it. Right? This is more or less the code you would write. Right? You would test whether the balance is enough to support the withdrawal, and if so, you would update the balance with whatever remains. And this is a fine piece of code in a sequential setting, but not in a concurrent one. In particular, if you have two of them running in parallel, you can run into trouble. Right? To see this, you can think of a very simple execution. Here, you start with a balance of 8. First, you go on the left, you test whether the balance suffices. It does. 8 is larger than 5. You perform the same test on the right. It goes through, and then you proceed with withdrawing 5 on each side. And now you have a negative balance, and this should never happen. Okay. So these kind of bugs arise in concurrency because we have no control over the scheduler. Right? They're often called Heisenbugs because they're very hard to reproduce by testing. So if we want to reason about correctness of concurrent software, we have to use some formal method. So a bit about the concurrency setting I'm using here. We have a bunch of deterministic processes. They run in parallel, and they communicate with each other over shared memory. There is no randomization, and all inputs are fixed. So really, all the non-deterministic behavior comes from the scheduler. Right? And our goal is to do some kind of local state reachability. Think of catching assertion violations for now. So the underlying algorithmic problem here is one in which we just visit every local state of every process, and we test whether it has a bug or not. We are in the explicit state setting, which means that your algorithm will deal with concrete states of the system. So we have a lot of them, and every encounter of a concrete state must be handled fast. And we're also stateless, which means that your algorithm cannot remember every state it has visited so far. It can only remember a few of them. You can think of constantly many, for example. Of course, there's a simple solution to this problem: examine all possible traces. But since there are exponentially many, we hope to try to do better, at least in some cases. Right? And one very, very standard way of doing better is partial order reduction, which is, again, a trace-based exploration of the system behavior. So let me try to give you a flavor of this. Partial order reduction relies on the notion of commutativity. So if you have a trace and you have a pair of events in this trace, we call such a pair non-commutative if both events belong to the same process or they both access the same shared memory location and at least one of them writes to that location. The idea here being that if you have a trace and you find an adjacent pair of commutative events, you can swap them without affecting the execution further down the trace. So you create a new trace which is in some sense equivalent to the first one. Right? And this notion of equivalence has been known as the Mazurkiewicz equivalence. So T1 and T2 are Mazurkiewicz equivalent, and we write it like this here, if they consist of the same set of events, and and they agree on the order of every non-commutative pair. Right? So E1 happens before E2 in T1, if and only if it also happens before E2 in T2. That's the idea. So pictorially here we have our trace space, and we partition it into a number of classes using this equivalence. Right? And we know that partitioning is sufficient for our purposes, meaning that you can simply pick a random representative in each class, and whatever conclusion you make about that trace carries over to the whole class. So in the end, you don't have to examine all possible traces, but you have to examine all possible classes in this partitioning. And hopefully, this number here is much smaller than this one. That's the idea. So let's focus on two processes for now. I'll be explicit about switching back to more than two later. And let me try to give you the idea behind our work through a simple example. Say we have this simple concurrent system. It consists of two identical processes, P1, P2, and each one of them first writes to a global variable x, and then it reads from it. Right? And let's look at two different executions of this system, T1 and T2. So in T1, the first process executes and completes, and then the second goes. And in T2, we have the inverse scenario. The second process goes and completes, and then the first one. Right? And you can quickly see that these two traces are Mazurkiewicz inequivalent because, well, we have changed the order of the non-commutative rights. Okay. But if you think a bit about it, well, the two traces are guaranteed to lead to the same system state, and this is because, well, in both traces, each read observes the same right. So this R1 here observes W1 both here and here, and this R2 here observes W2 in both traces. And this is really the key idea behind our work. We would like to say that if we have two traces and the two traces, and in each of them, every read event observes the same write event, we would like to treat them as equivalent, even though they might not be in a Mazurkiewicz sense. Right? So a bit more formally here, we have a trace T, and we define its observation function to map every read of the trace to the right that it observes. Right? And then we say that two traces are observation equivalent, and now we write it like this, if, again, they consist of the same set of events, and moreover, they agree on their observation functions. So every read observes the same right in both. So again, we have another partitioning of the trace space, which is also sufficient for our purposes. And now, the key result in the paper comes in the form of three theorems. Theorem 1 states that the Mazurkiewicz equivalence refines the observation equivalence. In other words, the observation partitioning will never have more classes than the Mazurkiewicz partitioning. Right? Theorem 2 states that you can go even further. The observation equivalence can become even exponentially coarser than the Mazurkiewicz one. Right? So you go from a situation like this in the Mazurkiewicz partitioning to a situation like this where you have collapsed a certain number of, even exponentially many Mazurkiewicz classes into one big observation class. And theorem 3 states that there exists an algorithm which explores every class of this partitioning once, and it spends only polynomial time for doing so per class. Right. So let me try to give you some intuition behind each of these. Actually, they're not that easy. Theorem 1, Mazurkiewicz refines observation. How can we reason about this? Well, let's look at two traces, T1 and T2, and they fall into different observation classes. Right? So this means that they must disagree on the observation of a common read. Right? So we have read R here, it observes W on T1, and it observes some different W bar on T2. And we ask ourselves, where can W appear in T2? Case 1, it appears to the right of R. But in this case, we have changed the order of R and W. Case 2, it appears to the left of R. But since R observes W bar, the W has to appear also to the left of W bar. So we split cases again. Case 2A, we have changed the order of W and W bar in T2. Case 2B, we haven't. This means that W bar appears after W also in T1, in which case you're also guaranteed to find W bar after R. Right? And these three cases cover all the possibilities, and we know that in each one of them, we have changed the order of a non-commutative pair. Therefore, the two traces are also inequivalent in the Mazurkiewicz sense. QED, easy. Theorem 2. The observation equivalence can become exponentially coarser than the Mazurkiewicz one. Well, let's look at this toy example. Here we have two processes. They're identical. Each one of them performs a sequence of write accesses to some global variable x, and then it reads from x. And if you do some basic counting here, you will find out that the observation partitioning has only linearly many classes, whereas the Mazurkiewicz partitioning has exponentially many. This proves theorem 2. Easy. So what about theorem 3? Well, this is a bit more involved. So bear with me. We'll need a few more slides. Let's change our focus for the moment, and let me draw your attention to like a core algorithmic problem that arises very naturally so far, which is the following. I give you an observation function, so a map from reads to writes, and I'm asking you to construct a witness trace that realizes the observation function. Or tell me that no such trace exists. That's also possible. So how fast can you solve this problem? A moment's reflection will reveal that this is not easier than our initial problem, because you can use observation functions to encode assertion violations. So instead, we'll focus on a slightly simpler problem, which is that of realizing what I call here well-formed observation functions. And we won't bother ourselves with a precise definition. It suffices to tell you that a well-formed observation function specifies a unique execution for every process in our system. So out of an observation function, we can get back one local trace for each process. And moreover, we guarantee that if there exists a witness trace of this observation function, then it must be an interleaving of these two local traces. Right? Or in the vocabulary of partial orders, we have a partial order here, and T will be a linearization of this. Right? Now, of course, not any such linearization will do. It needs to meet a number of constraints. In particular, it needs to meet observation constraints. If I know that R is to observe W, then I need to make sure that W happens before R. But this is easy to enforce, right? You just throw in some extra happens before edges. The second type of constraints is sequential consistency constraints. So if I want to make sure that R observes W, then for any conflicting W bar here that happens before R, I need to ensure that it also happens before W, so that it doesn't get stuck in between and change the observation. Right? And these constraints are also somewhat easy to express using 2SAT because, well, all they're saying is if A, then B, and this is a clause with two literals. Now, this being a partial order, the third type of constraints we need to enforce is transitivity constraints. Right? If E1 happens before E2 and E2 happens before E3, then make sure E1 happens before E3. But at the first glance, this is bad, right? Because it looks like now a 3SAT. We say if A and B, then C. And this is a clause with three literals. But recall that we only have two processes in our system, right? And you can easily reason about the following. For two processes, every triplet of events must already have an ordered pair. This is the pair that belongs to the same process. Right? So if we are to deduce that E1 happens before E3, we don't know this already, which means that either E1 happens before E2 already, in which case we get rid of the first condition, or E2 happens before E3 already, in which case we get rid of the second condition. Right? In either case, we're happy because we're back to 2SAT, right? We're again saying if A, then B. And you can show that these three are the only kind of constraints that your linearization needs to meet for it to produce a witness trace. So we end up with a theorem which says that, well, for two processes, realizing a well-formed observation function only requires polynomial time by going through this 2SAT encoding. Right? Fine. So now, having solved this core algorithmic problem, we're going to use it as a black box to guide our exploration of the observation partitioning. Right? So in particular, this is going to be a recursive process, so we will view it as a tree. And in every node of the tree, we're going to be constructing an observation function using our previous theorem and the algorithm that comes with it to get back a witness trace. We're going to look into the trace, construct a new observation function, and so on. So in the root, we start with an empty one, so no constraints. And while we are at some node U, we have some observation function O of U. We use the previous theorem. We get back a witness trace T of U. And now we perform a mutation step. We iterate over every read in the trace that does not already appear in the observation function. So we haven't fixed the observation of this read. And moreover, we iterate over every possible write event in the trace that this read could observe. And we simply strengthen our observation requirements here with this new read to write pair. Right? And we proceed recursively. We have another pair, a green one, a blue one, and we go recursively, and so on. And now this process is enough to guarantee completeness, namely that this way you visit every observation, every class in your observation partitioning. However, it's not optimal yet because you might be realizing the same observation function twice, right? For example, here, notice that T5 and T7 are witnesses of the same observation function. They have both acquired the red and the green observation constraint, just in different order. It turns out that you can get rid of this behavior by doing some very local bookkeeping, which doesn't really affect neither the space you use nor the running time. And at this point, we are ready to actually prove that this algorithm with the bookkeeping is the algorithm we're after. Namely, the algorithm explores every observation function once, and the total time for doing the full exploration of the partitioning is polynomial in the input times the size of the partitioning. Fine. So what happens when we go to more than two processes? Well, unfortunately, realizing a well-formed observation function is NP-complete in general, which strongly hints that we either need to give up on our desires for polynomial time, or we have to use a different partitioning, right? Not as coarse as the observation one. Actually, we can make a more refined statement based on the communication topology of the system. And what I mean by communication topology essentially is the following. You have an undirected graph. You have one node for every process in your system, right? And you draw an edge between two nodes if the corresponding processes communicate over some common global variable. So if P1 and P2 both access a global variable x, you have an edge between them. Right? And the distinction I'm going to make here is whether these graphs have cycles or not. Right? If we're in the case of cyclic topologies, think of like two processes, pipelines, stars like a server with multiple clients, then whatever I mentioned so far about two processes carries over without any change. The algorithm is optimal for the observation partitioning, and it runs in time polynomial in the size of the input times the size of the partitioning. Now, if you go to arbitrary topologies, like ones which can have cycles, like cliques, for example, then we relax our conditions on the partitioning. So the algorithm is now optimal with respect to another partitioning, which I call here tilde, which in terms of coarseness lies between the Mazurkiewicz and the observation partitioning, and it remains potentially exponentially coarser than the Mazurkiewicz partitioning, right? And the time required for covering the whole space is again given by a similar expression, polynomial in the input times the size of this new partitioning, right? Unfortunately, I don't have enough time to tell you how we do this. Maybe you can ask me afterwards, or we discuss it offline. Oh, yeah, and one comment about space usage here. Our space usage is always polynomial, right? And this has been historically a challenge. Fine, so we have some prototype implementation of this, and we have also conducted a few experiments. We have implemented our data-centric approach on top of NeedHub, which is a powerful stateless model checker for handling C programs. And we have conducted a few experiments comparing our approach with source DPOR, which was proposed about 4 years ago and was already implemented in NeedHub, so we didn't have to do anything about it. So I'll show you a few of them now. Here we have a synthetic benchmark which mimics some sort of optimistic locking mechanism. So we have two processes, and each one of them will attempt to lock a number of times, and if it fails, it exits. So the numbers in the parentheses here show the number of attempts that you make. The middle column shows you the number of traces explored by each of the two methods. Right? So in our case, we have a much coarser partitioning than the Mazurkiewicz one. We explore much fewer traces, and this is also reflected in running time. We also have a few benchmarks from SVComp. So here we focus on benchmarks which we control so that we could control their size, by controlling some loop unrolling parameter. A few examples here. Again, we see that we explore fewer traces, and this takes less time. So yeah, even though our partitioning is always coarser, turns out we're not always faster. There are benchmarks for which we explore fewer traces, yet we're slower. Of course, our method for exploring each class is probably slower than the standard Mazurkiewicz approach. So that when the size of the two partitioning is comparable, then it turns out that we're slower. But it's okay for now. I mean, this is a new approach, and our algorithms and our implementation is nowhere as mature as the Mazurkiewicz methods, which have been around for well, a few decades. So I'll conclude here. I hope I have given you a new paradigm for performing stateless explorations. This is a data-centric approach instead of a control-centric that the standard Mazurkiewicz techniques use. It leads to coarser partitioning, and we have an efficient exploration of the partitioning. Thanks. Sure.
So I don't work in this area, so maybe this is a very naive and off-the-mark question. How long is this installation topology?
Well, yeah. So you might have. Okay, here are the cases where you find acyclic topologies, two processes, as I mentioned, right? This is a fairly common case. Well, you can have two processes. Yeah, you can have a server-client architecture, right? Okay, but you need to know this beforehand. If you don't, you assume the worst case, everybody communicates with everybody else. But even in that case, our approach creates a coarser partitioning. And this coarser partitioning actually reduces the problem to one where you have an acyclic architecture. So our solution goes through acyclic architectures. This is another important reason why they're part of my presentation. Right.